'Tis but thy lack of name that is my enemy. Thou art thyself, though not a mere equation. What is an equation? It is nor expression, nor inequality, nor arithmetic result, nor solution, nor any other part belonging to mathematics. Oh, be some other name. What's in a name? That which we call a rose by any other name would smell as sweet. So equation would, were it not equation called, retain that dear perfection which it owes without that title. Equation doff thy name, and for that name, which is no part of thee, become function.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, I will review function notation. The topics will include the definition of function notation, inputs versus outputs, the significance of the input as a placeholder, the importance of the parentheses in function notation, function naming conventions, common mistakes made with function notation, and the strengths of function notation as opposed to standard equation notation. So let's get started. We already know from our prerequisite material that a function is a relation, which takes a single input and returns a single output. However, it also gains a special notation. The first part of this definition basically says that y and x can be related to one another such that each chosen value of x forces y to be a single value. That is, it's just a function. Then we use the notation y equals f of x to kind of talk about that function. X is the input of the function and f of x is a corresponding output. For example, suppose we are working with the relation y is equal to 7x cubed plus x minus 1. Building a table of values, it seems pretty convincing that whatever we choose for x will only have a single corresponding output for y. Thus, this looks to be a function, and it actually is a function. Hence, we can exchange the given equation notation for the function notation. We go ahead and let y equal f of x, and we get f of x is equal to 7x cubed plus x minus 1. Essentially, all we're doing is trading out y for f of x. But there's more to function notation than this. Because the following function has x as its independent variable, we plug in values for x. The outputs, which we would previously have called y, are just called f of x now. Here's the table of inputs and outputs for this function. The input of 0 leads to an output of -1, the input of 1 leads to the output of 7, and so on. That last item in the table needs some additional discussion, and we'll come back to that shortly. Students often get confused when their professor replaces x with some other variable, but we do so because x is just a symbolic placeholder that we can trade out for any symbol, variable, or picture that we want. It's often more beneficial, actually, to replace x with a symbol more reflective of the situation at hand. For example, the following functions are all equivalent. In each case, you can read this as our function evaluated at something is equal to 7 times the cube of that something plus that something minus 1. This notation becomes incredibly powerful when you need to do so-called time shifts or adjustments to inputs. For example, we might need to evaluate our function at a point other than x or happy face. What if we needed to evaluate this function at t plus 1? The function notation gives a lot of power here because we can easily replace our input x with the new input t plus 1. Of course, it's completely expected that you simplify this statement using your prerequisite polynomial multiplication skills. Doing so results in the following. Remember, a good rule of thumb in math is that if you have previously learned a skill in your math courses that can be used to simplify a statement, then you're expected to use that skill. First of all, f of x does not mean f times x. This is a common confusion for students new to functions, and it is completely understandable. Those parentheses do not symbolize multiplication. Instead, they separate the function name, which is f, from the input value, x. Let f of x equal 7x cubed plus x minus 1. And consider the following cases. We have 2 times your function, we have f evaluated at 2x, we have f evaluated at x squared, and then we have that oddball at the end, the square of our function. Following the order of operations, a prerequisite skill, you really can't go wrong with any of these. The first case has us plugging x into our function. Once that's done, we multiply the result by 2. The second case has us multiply x by 2 first, and then plug that into our function f. In the third case, we end up squaring x first, and then plugging that into f. In our final case, we plug x into f. Once that's done, we square the result. Essentially, what I'm implying here is twofold. First, always follow the order of operations. And second, the parentheses in f of x are not multiplication. After I wrote the title of this section, I thought, I wonder if there are actually conventions where they name functions. Anyhow, most students are told that function notation is y equals f of x, and that's that. The truth is that functions come in all variety of names, but f is the most common introductory name. I often name functions like cost of m. That's like a function giving the cost of a car rental based on the number of miles driven. Or I might name a function wage of h, which is just returns your wage in terms of the number of hours that you work. Or we could use k of z, which represents the temperature in Kelvin based on the number of zebras within 20 miles. Part of the power of functions is the ability to create a name that is more representative of the situation in consideration. Also, don't be fooled by your instructor into believing that functions must be represented by a single letter like f, g, or h. Programmers around the world know this is just foolishness, and it has taken us traditionalists in mathematics a long time to catch up. There are quite a few mistakes made with function notation, and I could spend considerable time going over an exhaustive list, but here are the top 3 mistakes I see from students who are just learning functions. For this discussion, we're going to go ahead and let g of x equal 3x plus 1. This function's simple enough to get my point across without losing you in the peripheral mathematics. I've already mentioned that the parentheses in function notation do not imply multiplication. However, it needs to be stated again. I see it all too often when a student is asked to evaluate something like g of 2, that they take the function and multiply it by 2, resulting in 6x plus 2 in this case. If you're being asked to evaluate g of 2, this means plug 2 in for x in your function. Your answer should not have an x in it anymore. The true answer is 7. This is another warning I have already given, but no matter how many times I state it, students still make the mistake. So let's go ahead and consider g of 2 plus 1. Note, this is not g of 2 plus 1. In the latter case, we get 10. On the other hand, if we just consider g of 2 plus 1, we evaluate g at 2 to get 7, and then add 1. Our final result here is 8. Notice that these are not equivalent. This mistake clearly deserves the top spot, and you'd be hard-pressed to find a math professor who would disagree. Consider the following question, which commonly appears on exams that I write for my algebra students. Let h of x equal 2x squared plus x minus 1. And we're splitting this into 4 parts. Part A, evaluate h of 0. Part B, determine the value of h at 1. Part C, for what value or values of x is the output to this function 5. And finally, Part D, solve h of x is equal to 0. In all honesty, most students do fine with parts A, B, and C. However, part D is their nemesis. For part A, we just plug in 0 for x, and we get h of 0 is equal to negative 1. Part B has a similar challenge level. The value of h at 1 means the output of h when we plug in 1 for x. This yields 2. In part C, we're told the output is 5, so we need to find the input or inputs corresponding to this. Solving 5 is equal to h of x, we get the following. Note we have to use the zero factor principle here in our factoring prerequisite skills to finally get x is equal to 3/2 or x is equal to -2. While the mathematics is slightly higher in level of difficulty, students usually don't mess up here. But, as I said a moment ago, part D is where I catch most people. Solving h of x equals 0 means our output is 0, and we need to find the corresponding value or values for our input x. Solving 0 is equal to h of x, we get, again, via factoring and the zero factor property or the zero factor principle, x is equal to 1/2 or x is equal to a -1. Now, often what students do with this problem is they plug 0 in for x, getting an output of -1, but this is completely incorrect. 0 is an output here, not an input. If you can master understanding of why function notation is not multiplication, why we must always follow the order of operations, and what the inputs and outputs of a function are, then you should be fine with function notation. I want to wrap up our discussion of function notation with a brief talk as to why it is so important. There are several very compelling reasons to use function notation. First, if you're just learning functions for the first time, the top reason for you right now will be that function notation allows you to track inputs and outputs. I cannot stress this enough. If you're given a terrible equation and asked to evaluate it at, say, 5.1, there could be a lot of mathematical work required to get to your final answer. In the end, most people answer with y is equal to 23.44 in this specific situation. Or they might not even answer with y equals 23.44. They just might get down to equals 23.44 like I did here. However, the person to whom you're handing the solution might also want to know the input that you used to arrive at that solution. If you did a lot of work, that input value might be hidden and difficult for you to remember or even to find. On the other hand, if you use function notation, you would generally answer f of 5.1 is equal to 23.44. This tells the reader that you plugged in 5.1 and the output was 23.44. Second, it creates a uniquely defined, reusable equation. This becomes more important as you move forward in science, engineering, or really anything technical, because you'll often have to juggle multiple equations at once. For example, if you're working on a project for your employer and you need to have 20 equations, each, let's say, representing the cost of a different insurance plan in thousands of dollars based upon the number of employees enrolled in the plan. Well, it'd be terrible to have them assigned to the same output variables like this. Without assigning a better naming convention, you would tell your employer that her company with 10 employees would have to spend either $28,000, $71,000, or whatever on insurance plans, but finding out which plan belongs to which equation is pretty much impossible. If you had created a naming convention like this, then the confusion has gone away. The cost of the Kaiser plan when you have 10 employees is $28,000. It's very easy to see with the function being named properly. Third and finally, function notation allows us the freedom to have a base recipe where the ingredients are not only allowed to change numerically, but also with dynamic conditions based upon demand. This is advanced, but very powerful. It's also probably easier to see than to explain. We have all used recipe apps or recipe sites in the past. Really good ones will ask how many people are being served and return the recipe. This is essentially a function. The amounts for the recipe and the cooking times change based upon the number of people, n, being served. For example, R of 10 would be the recipe if you're serving 10 people. But what if you knew that this dish was delicious and people generally eat 2.5 servings? Moreover, what if for every 2 guests there's an additional child who will eat only half a serving? Finally, what if you need 6 extra servings for friends who don't RSVP? Well, if n is the number of invited guests without kids, then those guests are eating 2.5n servings. For every 2 guests, we need an additional half a serving for their kid. So this would add half of n over 2, or in other words, n over 4 servings. You can check that, by the way. The n over 2 just basically says if you have 2 people, they brought one child. If you had 4 people, they brought 2 children together. But the children only eat half a serving. And finally, we're going to go ahead and add 6 servings for rude people who just show up unannounced. The total number of servings is therefore 2.5n plus n over 4 plus 6. When we reduce that down, that's just 11/4 n plus 6. But what are we going to do with this? Well, that's the actual number of servings that we need. Thus, we can determine the recipe by evaluating r of 11/4 n plus 6. Again, this may seem advanced, but it is really important. Well, thank you for watching this short video on function notation. As always, this content should be prerequisite to the course in which you're currently enrolled. If you found this material unfamiliar, or if it was confusing to you, then I recommend you click on the provided relevant prerequisite links listed below for further help. However, if you find you're continually doing this, you might want to consider speaking with your instructor about other course options. On that note, I sincerely hope these videos help you achieve success in your transfer level math and science courses. Cue the music.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.